What if I told you there is a $1 million prize attached to a question that looks almost like a calculus exercise? Where can one function equal zero? That question is the Riemann hypothesis. But the $1 million is not really about finding zeros for their own sake. The catch is that this function secretly knows about every prime number. Here is the real mystery. The primes are the atoms of arithmetic. Their individual gaps jump around unpredictably, but viewed from far away, their distribution becomes astonishingly regular. So forget the $1 million for a moment. We want to understand the bridge. How can a sequence made from whole numbers possibly be controlled by a function of a complex variable? Before worrying about zeros, we need to find the primes inside zeta itself. Start in the one region where zeta can be written with no advanced machinery. Take s equal to sigma plus it, and add 1 over n to the s for every positive integer n. If we temporarily set t to 0, we can actually draw a slice of the function. Near sigma equals when it shoots upward, farther right it settles toward 1. This is a real slice of zeta, not just a pair of axes. But s is allowed to be complex. Then zeta takes one complex number and returns another. So an ordinary y equals f of x graph is no longer enough. A complex function is a machine from one plane to another. So let us literally watch zeta work. I will move s upward along the safe line sigma equals 2. On the right, the point zeta of s moves through its own complex plane. That sine curve is the function being drawn, not as a height, but as the path of its complex output. The $1 million question begins when we ask whether this moving output can land exactly on the origin. But before zeros can tell us anything about primes, the primes themselves have to enter the story. For real part of s greater than 1, Euler's product can be proved directly. We will remove composite contributions from the zeta series 1 prime at a time. Multiply zeta by 2 to the minus s. That shifted copy contains exactly the even index terms. Subtract, and every even integer disappears. Repeat with 3. Its shifted copy selects the remaining multiples of 3. Subtract again, leaving only integers divisible by neither 2 nor 3. Continue through every prime up to p. Only indices with no prime factor at most p survive. As p tends to infinity, every integer larger than 1 is eventually removed, leaving only 1. Absolute convergence for sigma greater than 1 is what makes these rearrangements legitimate. So zeta times the prime product equals 1, giving Euler's product. It is unique factorization translated into analysis. Define lambda to equal log p at a prime power p to the k, and 0 otherwise. Psi of x is the sum of these weights up to x. For psi of 10, 2 contributes at 2, 4, and 8, 3 at 3 and 9, 5 and 7 once. So psi of 10 is 3 log 2 plus 2 log 3 plus log 5 plus log 7, or log 2520. In fact, psi of x is the logarithm of the least common multiple of the integers up to x. It records each prime once for every power that has appeared. Now take the logarithm of Euler's product. The product becomes a sum, and minus log of 1 minus z expands as z plus z squared over 2 plus z cubed over 3 and so on. Differentiate in s. The derivative of p to the minus ks contributes minus k log p, canceling the 1 over k. Every prime power therefore carries coefficient log p. That coefficient is exactly lambda of n. So the coefficients of minus zeta prime over zeta are precisely the jumps accumulated by psi. Start with the geometric series. It converges only for magnitude of z less than 1, where it equals 1 over 1 minus z. Outside the disk the series diverges, but 1 over 1 minus z still exists except at z equals 1. The series was only a local formula for a larger analytic function. And analytic continuation is rigid. By the identity theorem, two analytic extensions that agree on an open region must agree everywhere they both continue. Zeta behaves similarly. Its Dirichlet series works only for real part greater than 1, but other analytic formulas continue the same function beyond that half-plane. The continuation reaches the whole complex plane, except for a simple pole at s equals 1. We will skip the construction. What matters is that it agrees with the original series where that series converges, and analyticity makes the extension unique. Now the question about zeros finally reaches the region where the mystery actually lives. Now repeat the same experiment on the critical line, sigma equals 1/2. The point on the left climbs. The cyan point on the right is the actual value of zeta. At height 14.1347, the output hits the origin. That is a 0. Then at 21.022, it happens again. These are not dots we placed by hand. They are where the zeta curve itself crosses 0. There are easy zeros at the negative even integers. Those are called trivial. The non-trivial zeros live in the critical strip, and the functional equation forces them into mirror symmetries across the real axis, and the line sigma equals 1/2. Now the bridge is exact. Minus zeta prime over zeta has coefficients lambda of n, and psi of x is simply the partial sum of those coefficients. Perron's formula reconstructs a cumulative sum from a Dirichlet series. For x away from a jump, it gives psi as this vertical complex integral. We will not derive the contour integral here. A contour shift argument then shows that psi equals a main term x, minus a sum over the non-trivial zeros row, plus explicit lower order terms. We will use this result without proving the contour step. The pole at 1 gives the smooth term x. Each non-trivial zero row contributes minus x to row over row. This is exactly where zero locations enter a prime power counting formula. At this point, Riemann's question no longer looks arbitrary. The real part of each zero will control the size of a term in the prime counting error. So where can those real parts be? Riemann guessed the strongest possible answer compatible with the symmetry. Every non-trivial zero has real part exactly 1/2. Not most. Not 99.9%. Every single non-trivial zero. Now we can finally see why that horizontal coordinate matters. Pi of x makes a staircase. The prime number theorem says that from far enough away, this staircase follows the smooth curve x over log x. Hadamard and de la Vallée-Poussin proved this in 1896. And already, their proof depended on zeta. They showed it has no zeros on the line sigma equals 1. For the explicit formula, use the weighted counter psi that we introduced earlier. Its main trend is even cleaner. Psi of x is approximately x. So the real mystery has been compressed into one object, psi of x minus x. Take one non-trivial zero, rho equals beta plus I gamma. Its contribution contains x to the rho. Since x is positive, x to beta plus I gamma becomes x to beta times e to I gamma log x. The two coordinates of the zero now have different jobs. Gamma creates rotation as log x changes. Pair conjugate zeros, and those rotations combine into a real oscillation. Beta controls the growth envelope x to beta. Move beta from 1/2 toward 0.78. The frequency stays fixed, but the oscillation can grow much faster. That is why horizontal zero position matters. So gamma controls oscillation, while beta controls its scale. That is the concrete meaning of zeros, controlling prime fluctuations. Now imagine even one zero, with real part 0.8. Its term carries an x to the 0.8 envelope. That can overwhelm the square root scale we would get from a zero on the middle line. RH forbids every such intruder. If every beta is exactly 1/2, the zero contributions all live on the same basic square root envelope. One standard consequence is psi of x equals x plus an error of order square root x times log squared x. So the hypothesis is not a decorative claim about a vertical line. It is a global limit on how violently the primes can deviate from their smooth average behavior. Computationally, the picture is almost hypnotic. Every zero we have drawn sits exactly on the critical line, and numerical verification goes vastly farther. Proof progressed much more slowly. Hardy proved infinitely many zeros lie on the line. Selberg proved a positive proportion. Levinson reached 1/3. Conry passed 2/5. By 2020, later work had pushed the record beyond 5/12, about 41.7%. And this distinction is crucial. Checking more and more zeros is evidence. Proving that a guaranteed fraction lies on the line is mathematics. Neither one is the same as proving every zero lies there. Then, on August 10, 2026, Anthropic reported a dramatic new result. An unreleased research version of Claude produced an argument raising the unconditional lower bound from roughly 41.6% to roughly 67.2%. The accompanying paper gives the optimized constant 67.25%. This is not a numerical statement saying Claude checked 67% of the zeros. It is a mathematical lower, bound on the asymptotic proportion that can be certified on the critical line. And the missing 32.8% are not known counterexamples. This result simply does not determine where they all are. The paper explicitly does not prove or disprove RH. For nearly half a century, the guaranteed proportion crawled upward, beyond 1/3, beyond 2/5, then just beyond 5/12. The reported 2026 result is not another tiny decimal improvement. It leaps to 0.6725, a gain of roughly 25.6 percentage points over the 2020 record. Within this specific proportion problem, that is enormous. But percentage progress and RH live in different logical worlds. RH does not ask for a large fraction. It asks for every zero. Now the status check, because this result is only 2 days old. Anthropic has released the paper and says 2 mathematicians at Anthropic studied and validated it. Brian Conry and Dan Goldston also examined the work on short notice. But 2 days is not enough time for a result of this scale to acquire broad independent consensus. So as of August 12th, I am calling it exactly what it is: a reported breakthrough whose wider scrutiny is still unfolding. There is one subtle point that matters enormously. Imagine that among the first 100 zeros, just one lies off the line. Then 99% are on it. Now suppose among the first 1,000, there is still only one exception. That is 99.9%. And among 100,000, even 10 exceptions still leaves 99.99% on the line. That is what a density statement can do. The fraction of offline zeros can tend to zero even if rare exceptions keep appearing forever. So 100% in asymptotic density means that exceptions become negligible compared with the total. It does not mean that the exceptional set is empty. For RH, the distinction is simple. 100% in asymptotic density still does not say that the exceptional set is empty. This is a statement about counting density, not Lebesgue measure. In an upcoming video on measure theory, we will develop the broader language for making the idea of a negligible set precise. Even one genuine exception would make the Riemann hypothesis false. Follow the thread one last time. We started with primes, irregular 1 by 1, regular in the large. Euler's product put those primes inside zeta. The logarithmic derivative turned prime powers into coefficients, giving us the weighted counter psi. When complex analysis reconstructs psi, the zeros appear as correction terms. Their imaginary parts create oscillation. Their real parts control how large those oscillations can grow. Riemann's hypothesis says every non-trivial zero has the one real part that keeps those fluctuations on the critical square root scale: 1/2. A single genuine zero off this line would destroy the hypothesis. As of August 12, 2026, the reported guaranteed proportion on the critical line has jumped to roughly 67.2%. That is a remarkable advance. But logically, the million-dollar question has not changed at all. Are there any non-trivial zeros off the critical line? There is still $1 million prize attached to a proof. But the deeper reward would be a final explanation of just how regular the prime numbers are allowed to be.